So hi there, everybody. I'm Dan Frost. I'm the president of the European Association of Geochemistry. I hope you're all enjoying the meeting. I hope you're having a good time. Lots of science and lots of talks that are interesting for you. Funny thing happened, right? I was in the session yesterday. Somebody was taking a few pictures of the slides, and I think in the end, he took a picture of every single slide. And I went up to him afterwards and I said, "You know we record these, right?" You know, and I talked to a couple of other people, and they said, "No, they don't." And I said, "Yeah, no, we record them." And he said, "Look, there's no camera here. There's nobody filming this. There's nothing, you know." And I said, "Yeah, it's recorded on the computer. It's the PowerPoint slides are available, and the audio is being recorded." And it made me realize that a lot of people don't kind of realize that, you know. They stand up at the podium, and they don't realize we're recording it all. So the next day, you can, if you feel that you missed something, I mean, that was always how it was in Goldschmidt. People would always complain. They say, "Oh, they scheduled these two sessions at exactly the same time," and well, there's no reason to worry about that now, right? So you can go online 30 days after the meeting, and you can watch all of those things that you might have missed. And I just get the feeling that people perhaps don't recognize that. So anyway, back to what I'm supposed to be saying. What is that? Collaborations with other societies is a key building block to build a strong geochemical community. And therefore, it is a really great honor to have several societies that present their awards at the Geochemical Conference, at the Goldschmidt Conference. So I'd like now to invite Wei-Dong Sun from the Shen-su Sun Foundation.
Good morning, ladies and gentlemen. I'm Wei-Dong Sun from the Chinese Academy of Sciences. I also serve as the secretary of the Shen-su Sun Foundation. Shen-su Sun Foundation set up the Shen-su Sun Medal and Shen-su Sun Lecture. The Shen-su Sun Award is designed to recognize geochemists under the age of 40 who works in mainland China, Taiwan, Hong Kong, and Macau. This year is the 20th anniversary. We have so far 19 awardees. And this year's award goes to Jihua Hao, in Chinese, Hao Jihua, Professor Hao Jihua, to recognize his contribution to the recycling of nutrients in early Earth, in the heading Earth, and also in ice, moons, and other planetary bodies. So let's welcome Jihua. Thank you, everyone.
So I now invite Isabelle Danielle from the European Mineralogical Union.
Hello, everyone. I'm here in my capacity of the European Mineralogical Union president and to present the EMU Research Excellence Medal. This medal is presented to young to mid-career scientists who have made significant contributions to research in mineralogy and whose professional and societal activities contribute to strengthen scientific links within Europe. In 2024, it goes to Marta Pamato and Jakub Plesil. A few words about Marta. Marta Pamato is a professor at the University of Padova in Italy, and she has emerged as a new leader in the field of crystallography and mineralogy by making cutting-edge experiments on deep earth materials and their primordial geophysical and geochemical significance and consequences. Her scientific achievements are selfless cooperation at an international scale, her dedication to the next generation of mineralogists across Europe make Marta a talented recipient of the European Mineralogical Union Research Excellence Medal. Marta. So in 2022, we had 2 medalists. Jakub Plasil is the next one. So Jakub is from the Institute of Physics of the Czech Academy of Science. He's an exceptional gifted mineralogist and crystallographer who tirelessly works to decipher the complex crystal structures and environmental impacts of uranium-bearing phases. Over the years, he has strengthened the European network of mineralogists, and for the relevance and international dimension of his work, Jakub Plasil is truly worthy to receive the European Mineralogical Union Research Excellence Medal 2024. Jakub.
I now invite Dorrit Jakob from the International Association of Geoanalysts.
Good day, everyone. My name is Dorrit Jakob, and I'm here in my capacity as the president of the International Association of Geoanalysts. Our awardee for this year's ECR award gave, by the way, a brilliant lecture on Tuesday afternoon for those who have missed it there, but as I hear, they are being recorded, so please go back and listen to her lecture when you have time. The International Association of Geoanalysts promotes the advancement of geoanalytical science and supports the professional needs of those involved in the analysis of geological and environmental materials. Every year, the IAG bestows the Early Career Research Award for Excellence in Analytical Geochemistry to recognize these contributions from early career scientists. Eligibility is limited to scientists who are currently pursuing a higher degree with a focus on geoanalysis or who have completed their university education within the past 5 years. We are now accepting nomination for next year's award for all of those who are interested here. Dr. Xiuhong Liao is the recipient of the 2025 Early Career Research Award in recognition of her contributions to geoanalysis. During her PhD candidature, Dr. Liao developed a laser ablation solution sampling methodology for MCICPMS. This technique overcomes the limitations of traditional nebulization by improving analyte transport, reducing interferences, and minimizing sample consumption. She has successfully applied this methodology to a range of geological and environmental materials since, and expanded her focus on the development of much-needed reference materials for isotopic and environmental analysis in gemology. I'm pleased to welcome Dr. Xiuhong Liao to receive the prestigious IAG Early Career Research Award. Xiuhong.
And finally, I invite Avner Vengosh and Shen-su from the International Association for Geochemistry.
Hello, everyone. My name is Avner Vengosh, and I'm Vice President of the International Association of Geochemistry. And if you don't know about us, we have a booth here. Visit and see what we are doing. We are very honored and pleasure to present here today the Jinjin Fu Memorial Lecture, and I think the better person to present this award will be my colleague, Zhenju.
Thank you, Evan. I'm Shen-su from Indiana University in the US. It's my great pleasure to introduce the Jinjifu Memorial Lecture at the International Association of Geochemistry. The lecture was established to honor my undergraduate mentor, Professor Jinjifu, but also to inspire early career scientists to pursue rigorous research in geochemistry. The lectureship will recognize an outstanding early career scientist from any country within 10 years receiving their PhD. The awardee will deliver a keynote lecture and receive a small travel grant. The honor not only celebrated Professor Jin's legacy, but also embody IAGC's mission of fostering research excellence. This is a third award.
And for this year, we are honored to have the awardee for Dr. Merit Apley. She is a tenure-track assistant professor at the EPFL and a nominate for the Jinjifu Early Career Lectureship Award for her outstanding work on soil biogeochemistry. Her research focuses on redox processes and soil carbon stabilization with substantial implication for climate change mitigation. Since joining the EPFL in 2022, she has established a cutting-edge research program and published extremely top-peer journals. Dr. Apley's academic path includes distinguished degree from ETH Zurich and a postdoctoral fellowship in Stanford University in the US. She received the ETH Medal for her groundbreaking PhD work on the reactivity of iron minerals. As a leading female scientist and mentor, she serves an inspiration role model in the field of environmental geochemistry. And Merit, please join us.
So then perhaps another round of applause for all the awardees for this morning. Yeah? So I'd like to now welcome my colleague, Liz Sykes, the president of the Geochemical Society, to co-present the P.W. Gast Lectureship Award. So the Gast Lecture is named in honor of Paul Gast, a pioneer in the application of rare earth elements to geochemistry, who was also chief lunar science advisor to NASA during the Apollo program. So this prize is jointly awarded by the European Association of Geochemistry and the Geochemical Society to recognize a mid-career scientist for outstanding contributions to the field. And it's celebrated each year through this lecture at the Goldschmidt meeting. And it's my great pleasure to introduce the 2025 Gast Lecturer, Professor of Geochemistry and Planetary Science at the University of Cambridge, Helen Williams. Okay, right, yeah. So Helen exemplifies the spirit of curiosity and discovery that this award celebrates. And throughout her career, she has continuously developed the use of non-traditional stable isotopes to address some of the most pressing and important outstanding questions in solid earth geosciences. And when you look through her work, whether it's applying the use of iron isotopes to study the redox state of the mantle, or applying new methods in molybdenum isotopes to examine the formation of the continental crust, or zinc isotopes to study fluid transfer at subduction zones, you really do start to get this sense of adventure that she's alluding to in the title of her talk today. So Helen studied geological sciences at Cambridge and received her PhD from the Open University. She then went to ETH to work with Alex Halliday, and then after stints at Macquarie University and then Oxford, she became faculty at the University of Durham before moving to Cambridge in 2018. So beyond her own research, Helen has given exemplary service to our community, not only serving the GS and the EAG in a number of roles, but also, for example, co-organizing the 2019 Goldschmidt Conference in Barcelona. If you remember, that's the meeting that had the beautiful mosaic gecko logo, and that was Helen's idea. Yeah. So she's also been involved in early career workshops at Goldschmidt for many years now, and has been a long-term editor of Geochemical Perspectives letters. So Helen has been a recipient of 2 ERC grants. Her most recent ERC grant, advanced grant, Earth Melt, explores the chemical consequences of early planetary scale melting. So when we try to understand the formation and the earliest differentiation of the Earth, scientists generally turn to information that they can get from meteorites, as the consequences of these very early processes on Earth appear to have been erased by 4.5 billion years of geology. But Helen is focused on tracing the evidence of these earliest processes in the reworked geochemical record of the Earth using novel stable isotopes, helped along, of course, by modern multi-collector mass spectrometry, surely a great working group, and that keen sense of adventure. So please join me in congratulating Helen, who will give the Paul Gast Lecture entitled From Hard Rock to Heavy Metal, High Mass Stable Isotope Adventures in Mantle Geochemistry. Okay, I'll get out of the way.
So thank you all so much for coming here. So it's an immense honor to be here giving a lecture in the name of Paul Gast, the Geochemical Society's first Goldschmidt medalist. So Goldschmidt's a wonderful conference, and I've been going to this meeting since I was a PhD student in 2000. This means that nearly half my lifetime has involved Goldschmidt. You can do the maths. And I'm not sure whether I should be more scared by that or in fact be more scared by standing in front of you all giving this talk. But nonetheless, over these years, I've had the chance to encounter and work with many wonderful people, and I've learned from you, I've been inspired by you, and I've also become friends with many of you over the course of many Goldschmidt conferences. And I've attended these Goldschmidt meetings whilst, as Dan alluded to, working in a range of different places. In fact, spending nearly 13 years as a postdoc and as a research fellow. And so it's really nice, before I move on and talk about science, to speak to the PhD students and early career researchers in the room and say that you have all my encouragement and support on what can sometimes feel like a very stressful and uncertain journey. And I guess what I would like to say to you now is, if I can make it, then so can you. So what have I been doing all these years? So as Dan says, I'm an isotope geochemist, and I've spent much of my life looking at how we can apply high AMU, heavy stable isotope systems to try and address these broad-scale Earth and planetary science questions. My group analyzes these elements on plasma source multi-collector instruments. There are 2 of these instruments here, for example. And these instruments are my pride and joy, despite my husband, a geophysicist who once described Goldschmidt as a bit too much epsilon for him, once commenting to me that they resembled expensive filing cabinets. However, despite the slightly uninspiring appearance of these instruments, I'm deeply impressed at the level of engineering and design that's gone into these and what they have allowed us to do in the community, which in my case has been an awful lot of iron stable isotope measurements. Now, iron's a major element in silicate planets, in their mantles and in their cores, and it can take multiple oxidation states. It's this partitioning behavior and redox sensitivity of iron in its isotopes that has fascinated me over the years. And it's the isotope system that I'm going to focus this particular presentation around. And so in this talk, I thought it would be fun to lead you on an iron-stable isotope hunt for the Earth's missing magma oceans, and that has occupied me and my collaborators on this project for a while. So what do I mean by magma oceans, and what do I mean particularly by missing? So what is a magma ocean? It's considered to be the product of the near whole-scale melting of the silicate interior of a differentiated planet or planetesimal, which is likely an inevitable consequence of the energy released in the course of planetary accretion and evolution due to the short-lived isotope systems or indeed due to impacts. In fact, magma ocean events seem to be quite common in our solar system and are certainly documented on the Moon, on Vesta, and even implicated in Mars. Our planet's most recent magma ocean event is widely considered to result from the moon-forming giant impact. And so as you can see here in the simulations from this paper, irrespective of what particular kind of impact scenario you're considering, the consequence is the catastrophic melting of that planet's interior. And the subsequent cooling and crystallization of this magma ocean would have set our planet on a journey of no return towards its present-day internal structure, chemistry, oxidation state, and ultimately habitability. So this is an interesting problem, and as you might imagine, there are numerous scenarios that have been proposed to explore the process of magma ocean cooling and crystallization starting from about 4.5 billion years ago. The Earth is a large planet, so many of the proposed scenarios involve the crystallization of high-pressure phases, so Bridgmanite, ferropericlase, Dave-Mauite, for example, present in the Earth's lower mantle, of which Bridgmanite is the most abundant and hence most important. And this is just one example of a magma ocean crystallization here from a well-known paper that focuses on magma ocean crystallization starting in the middle of the lower mantle, so at pressures greater than 26 gigapascals, below roughly 170 kilometers depth in the Earth's mantle. So looking at this scenario in a little bit more detail, the reason why you have magma ocean crystallization taking place in the middle of the lower mantle rather than, say, at the top of the lower mantle is because the magma ocean adiabat, so these green curves here, so you can see them progressively moving to the left as we cool. Crystallization starts at the point in time when these green curves basically dip beneath the liquidus, so basically when we start to crystallize solid material. And now we don't obviously know the behavior of magma oceans or lower mantle phases terribly well, but if we think that the liquidus slope has this kink in it here, then this means that we can expect that magma ocean crystallization would have really started from this inflection point, dividing the remaining melt in the Earth's interior into an upper magma ocean and a basal magma ocean, the latter becoming more iron-rich due to the greater incompatibility, so preference for being in the melt phase, of iron with respect to magnesium in the main crystallizing silicate phases, Bridgmanite and ferropericlase. However, it should also be pointed out that this is just one magma ocean crystallization scenario. There are others. You could, for example, have crystallization going from the core mantle boundary to the surface here. And this particular scenario does not predict the presence of a basal magma ocean. And even if you did decide that you wanted a basal magma ocean, and rather than a surface magma ocean, there are still further complexities here. For example, there are variants on this scenario depending on whether you have a slowly cooling magma ocean, potentially because you've got an insulating atmosphere, or whether you've got a rapidly cooling magma ocean, and indeed the depth where your crystallization starts, whether it starts above or below the density compensation depth, the depth at which your crystals are less dense than the iron-rich basal magma ocean melt that forms as they begin to crystallize. And of course, these different scenarios make different predictions about the development and separation of the basal magma ocean and the stratification between crystals and melt, how stable these are. and ultimately the depth range at which bridgemanite crystals, mush or cumulate, accumulate, and the size and composition of the basal magma ocean. So why might this be important? So the overall motivation here is that we want to gain a better understanding of our planet's internal structure and evolution as it cools in the billion years following the moon-forming giant impact here. So you can see here, this is from a recent paper. This is just a model of the cooling of the Earth's interior here, where you've got the basal magma ocean. This is this pink circle here, progressively shrinking and crystallizing. As it does so, that has implications for the distribution of iron in the remaining mantle, and it also has implications for the distribution, critically, of heat-producing element. So all important things if we're thinking about our planet's chemical evolution and ultimately habitability. The presence of a basal magma ocean, and indeed the whole scenario of magma ocean crystallization in the lower mantle, it may also have a profound influence on planetary redox state. And that's because the phase bridgemanite, so MgFeSiAlO3, has this incredible affinity for ferric iron. It likes ferric iron so much that it forces ferrous iron in the lower mantle to disproportionate or split into ferric iron hosted in the bridgemanite and iron metal present here to maintain charge balance. Now, this is an incredibly exciting reaction, and it has the potential to be a major contributing process in explaining the oxidized nature of our mantle. However, oxidation is only going to result if we're capable of removing the iron metal produced into this reaction and extracting it into the core. The presence of a basal magma ocean may be particularly important here because iron metal drops will descend rapidly through a basal magma ocean. So this would facilitate the extraction of iron metal and ultimately the oxidation of the Earth's mantle. So hopefully, I've persuaded you by now that magma oceans are sort of cool things and that we ought to be interested in them. So the next question is, can we observe their presence on Earth? And here's the tricky thing. Now, there are large low shear velocity provinces. These are widely documented on Earth. This is just an example from a recent study. And it might be perfectly reasonable to say that these iron-rich domains could indeed represent the residual products from magma ocean crystallization. However, there are a lot of other things going on that could create either dense domains or iron-rich domains, so we need other complementary sources of information. And the problem that we have is that our planet has been tectonically reworked and tectonically mixed. And this is a little bit of a problem for us. We might think that we'd like to use rocks derived by partial melting of the Earth's interior to probe the chemistry of that interior and to interrogate those magma ocean crystallization processes. But there's a problem when our mantle has been mixed over billions of years. One way in which we can get around this problem is to focus on ancient mantle melts. We can use them as some kind of probe of not unmodified, but hopefully minimally modified mantle source regions. So we can try and see through these tectonic reworking processes to get some kind of understanding of the ancient processes that may have formed their particular mantle source regions. And so now these rocks have been studied extensively, as you might imagine, with particularly important constraints coming from the short-lived 146 samarium to 142 neodymium and 182 hafnium to 182 tungsten chronometers. For the non-isotope geochemists here, and I do appreciate that not everyone is an isotope geochemist, these are systems that have really short half-lives, the half-life being the time in which it takes for half of the parent isotope to decay. And the power of that means that within 5 half-lives, so roughly 500 million years in the case of 146 samarium, or 45 million years in the case of 182 hafnium, you don't have any parent isotope left. So you don't have any ability to create an isotopic anomaly, such that any excess or deficit in your daughter isotope, so be that 142 neodymium, or 182 tungsten, as in this example shown here, expressed in mu parts per million, any kind of excess or deficit tells us about a process that must have taken place really, really early on in Earth history. And so we can use these particular isotope tracers to give us information about metal silicate differentiation, potentially, in the case of the hafnium tungsten system, which is widely used to explain why we have positive mu-182 tungsten in ancient rocks as an ancient signature of metal extraction to form the Earth's core. Or in the case of 142 neodymium, where ancient rocks show excesses and deficits in this isotope anomaly, potentially telling us about ancient silicate partial melting processes. In contrast, long-lived chronometers, so now here we have the example of 147 samarium decaying to 143 neodymium and 176 lutetium decaying to 176 hafnium. These are really interesting to us because of these long half-lives. These parent isotopes will probably still be around long after our planet is not. And these isotope systems are particularly interesting to us because in most upper mantle phases, the behavior of the samarium and neodymium and the lutetium and hafnium system are coupled. And that's because the parent element is always more compatible than the daughter element, except for what I hope is now your favorite mineral, bridgmanite, where this behavior is inverted over a specific pressure range, where hafnium becomes more compatible in bridgmanite compared to other phases. And what this means is that this will invert the behavior of the hafnium and neodymium isotope systems. So on this plot here, which shows the time-integrated lutetium-hafnium ratio versus time-integrated samarium-neodymium ratio, most modern mantle melts, so mid-ocean ridge basalts, most ocean island basalts, lie on a broadly positive array here, created by the time-integrated effect of those upper mantle melt extraction processes. And this is widely referred to as the chondritic array, although it's worth bearing in mind that this is just really a model concept. Now, the key thing here, the key thing I want you to note, is that there are some ancient rock suites here, and I've made them different colors here, that lie off this array. And we think that this is due to the involvement of lower mantle material in their source regions. So in the case of these samples here, derived from the Isua supercrustal belt, generously contributed by Hanaka Rizzo and Morboye, these samples have a less radiogenic hafnium isotope signature than we might expect because of lower lutetium hafnium than we might expect in their mantle source region as a consequence of residual bridgmanite, whereas the opposite is observed for these two suites here, the Schappenburg and the Welterbraden Komatiite suites, generously provided to us by Igor Putel. So what do iron isotopes bring to the party? So iron is an essential structural component of major mantle minerals. Differences in iron bonding environment are manifest in stable isotope partitioning effects that we can measure. And critically for us, these stable isotope partitioning effects are driven by changes in oxidation state, where we might expect that mineral phases where you have ferric iron typically get enriched in isotopically heavy iron. So by that, I mean high 57 iron, high 56 iron relative to 54 iron. And in this talk, I'll be using a delta notation to express that. So high delta iron is an enrichment in isotopically heavy iron. And the corollary is where you have more reduced iron, so particularly iron metal here or iron in higher coordination states, you might expect to show an enrichment in isotopically light iron, and this will give you low delta 57, 56 iron ratios. So what do we know about iron isotopes so far? Well, we've got a pretty good handle on what we can expect in terms of their behavior during upper mantle processes such as partial melting, where we can use ab initio predictions of isotope fractionation and experimental data to model the partitioning of iron isotopes between ubiquitous mantle mineral phases melt. So in this particular figure here, you've got a pressure temperature grid for a typical mantle peridotite bulk composition. These are the phases of solid, solid and liquid, So as we go up temperature, we start to melt. And our models, which are based on the predicted assemblages of common mantle minerals over this predicted pressure temperature space, show that there's actually very little iron isotope fractionation during partial melting, such that the iron isotope compositions of igneous rocks will primarily reflect that inherited by their source regions, which is an incredibly useful thing to us. So what does this mean for the lower mantle? Well, the key aspect of iron isotopes that render them particularly suitable for tracing lower mantle processes is, first of all, the small magnitude of fractionation that we've talked about in the upper mantle, and also for the small magnitude, in fact, zero magnitude within error, of iron isotope partitioning between liquid iron metal and liquid iron silicate. But from experimental work that I did many years ago with Bernie Wood and John Wade, we know that isotopically heavy iron is concentrated in a bridgmanite relative to isotopically light iron in the iron metal that is produced by disproportionation under lower mantle conditions, where we have that oxidation and that incorporation of ferric iron by bridgmanite. So therefore, we can use iron-stable isotopes to trace the net accumulation or loss of these iron metal droplets produced by disproportionation. And so putting this all together, what we're going to try and do in this talk is we're going to try and trace the net accumulation or loss of iron metal droplets produced by bridgmanite disproportionation taking place in the lower mantle. And we're going to try and use this to see if we can place some constraints on magma ocean crystallization processes. So how do we do this? Well, now it's time to return to the filing cabinets. So hopefully, by this point in time, I've convinced you that iron isotopes are a really useful tool that we can use with other tracers to understand magma ocean crystallization processes. And we can use plasma mass spectrometers to try to get isotope data for well-characterized, carefully sampled ancient rock suites. And this is work that I've been doing with a number of people over the last few years. So we have Elsa Amsalem here. She's looking pretty happy. Her Neptune session is going quite well. And we have Simon Matthews here working on Isuameta basalts, who perhaps has a slightly more ambivalent attitude to mass spectrometry, which has been immortalized in a cartoon in the preface to a recent PhD thesis on iron isotopes in oceanic basalts, the cartoon being titled, "The Neptune is on Fire, Make of That What You Will." So now what I'm going to do in the rest of this talk is present the iron isotope data. And for simplicity, I'm going to keep things to these three suites that I've already introduced you to. So metabasalts from the Isua supercrustal belt, 3.72 Ga, possessing positive tungsten anomalies, positive 142. Schappenberg, the opposite, negative 142 neodymium, negative tungsten anomalies, and Weltevreden, a mixed 142 neodymium isotope signature, and sadly no tungsten isotope yet. And of course, these systems displaying these sample series displaying completely opposite but still decoupled lutetium hafnium and samarium neodymium behavior. So the first sample set I'm going to talk about in a little bit of detail are the 3.72 billion-year-old basalts from the Isua supercrustal belt provided to me by Hanneke Rizzo and Moboye. And these samples are really interesting, were really interesting to us because we saw a striking correlation between iron stable isotope composition here. So this is a stable isotope signature, it's completely time independent, correlating with mu-182 tungsten, which is the short-lived system which tells us about fractionation of hafnium from tungsten, a lithophile versus a siderophile element, in the first 45 million years of Earth history. And so we interpreted this particular correlation in terms of a mixing array with the basalt suite sampling an end member created within the lower mantle involving a bridgemanite cumulate to give us our isotopically heavy iron isotope composition here, and also in mantle that had been minimally overprinted by later addition of chondritic material potentially, so hence recording this positive mu 182 tungsten signature of early core formation or even early silicate differentiation. So now, turning to the new data here that we're writing up, we're going to look at these ISUA samples in the light of two other komatiite suites. We're now going to talk about two suites from the Barberton, the Veltevreden komatiite suites and the Schappenberg komatiite suites. And these samples were generously provided to us by Igor Poutel, who many of us know as being an expert on komatiite genesis. And here we have to be really careful and focus on spin effects and chilled margin samples because of the effects of residual olivine accumulation. So now doing this, here's our ISUA sample set for reference. First of all, we'll talk about Schappenberg, which is our most contrasting sample set to the ISUA series. And we can see here that whereas the ISUA samples were elevated, if you remember, to decoupled hafnium neodymium, showing this time-integrated excess of hafnium relative to lutetium, decoupled from the mantle lutetium hafnium samarium neodymium array, and Schappenberg lay on the other side of that array. We now see that they also lie on the opposing sides of the primitive mantle for iron stable isotope compositions, and yet they both display the same correlation with tungsten isotopes. So potentially, we could be looking at some kind of complementary melt and residue from magma ocean crystallization processes. So we can now move to a lithophile system, and where even though we don't see the same kind of strong correlation with iron isotopes, the broad complementarity of the ISUA, Schappenberg, and now Veltevreden samples remains the same. So here are those two end members that I introduced you to before here. So how do we interpret this data? That's what I really want to spend the remaining 15 minutes or so talking about. So the obvious thing to think about when you consider ancient rock samples, the first question that anyone always asks you about is alteration. And I'm certainly not going to try and persuade you that rocks that are over 3 billion years old are not altered. However, whilst it's known that tungsten in particular is a fluid mobile element, we obviously see excellent correlations between iron and tungsten isotopes. Iron is not known to be particularly mobile. It's a good thing. But we also see correlations between iron isotopes and middle to heavy rare earth elements, which are definitely not considered to be mobile. And these correlations are indeed likely explained by magmatic processes. We could also think about crustal contamination. That's something else that people often talk about when you look at isotope systems. But one of the things, and there are many things I love about iron isotopes, okay, but one thing I love about iron in particular is that its high abundance in igneous rocks means that you don't have blank problems in your chemistry, but it also means that you're remarkably resilient to crustal assimilation. Now, of course, if you say you're working on an Archean rock, the next thing that anyone says to you when you say that you're doing iron isotopes is they say, well, what about BIFs? Fair enough, I get it. But the BIFs emplaced that either contemporaneous or older than these Schappenberg komatiites, these 3.55 Ga komatiites, they're all isotopically heavy. In Schappenberg, we have really isotopically light signatures, in fact, ranging from values to sort of chondritic primitive mantle to values that are actually really subchondritic here. So never say never, but this, we think, is a really unlikely explanation for our iron, tungsten, and 142 neodymium isotope variations in the komatiite suites. Okay, so now Schappenberg suite in particular, has got negative tungsten, negative mu142, negative isotopically light iron isotope composition. Now 142 neodymium in particular tells us about silicate melt differentiation processes. And in fact, although it's not so frequently used in this way, the hafnium tungsten system could also reflect silicate differentiation because hafnium is generally much more compatible than tungsten, particularly in bridgemanite. So before we start thinking about magma ocean processes, we have to think about other silicate melt differentiation processes. What about recycling of ancient oceanic crust? It might have a negative mu182 tungsten signature and a negative mu142 neodymium signature. Or what about silicate melt metasomatism taking place in the upper mantle? But here we can turn to a slide that you've already seen now, and that's our predictions of mineral melt fractionation during upper mantle melting processes. And all the models that we've done, and in fact that other groups have done, I'm not the only person to work on iron isotopes, I'm in the mantle, predict that the stable iron isotope composition of melts will always be isotopically heavy with respect to the stable iron isotope composition of the residue. And Schappenberg has a light iron isotope signature. So Schappenberg does not look like a melt for iron isotopes, even if it might look like a melt for 142 neodymium and potentially tungsten isotopes. So I think we can comfortably rule out crustal recycling or melt metasomatism. I'm not saying that these processes don't occur, but I'm saying that they're unlikely to be viable scenarios for explaining the isotopically light signatures of the Schappenberg komatiites. So now let's talk about some other things that we need to think about when we're talking about siderophile elements like tungsten and like iron. So we need to think about contributions from the outer core, whether that's diffusion from the outer core that's been invoked to explain the negative tungsten isotope signatures seen in ocean island basalts, or indeed residual core material left over from the moon-forming giant impact, or indeed the addition of undifferentiated chondritic material to the Earth's mantle after the main episode of core formation had ceased. The consequence of all of these processes would be adding an awful lot of tungsten and an awful lot of iron. So both of these things could potentially give us, at least for tungsten, could explain this decrease in 182 tungsten through time, might even explain these negative 182 tungsten signatures seen in modern ocean island basalts. But of course, the question is, could either of these processes have been going on with our samples? And here, returning to our favorite plot here, is that the challenge here is that Schappenberg has got an iron isotope composition that's lighter than the primitive mantle, and it's lighter than chondrites. And yet, metal silicate partitioning experiments for iron isotopes done under a range of conditions by a number of very talented experimentalists and isotope geochemists all show us that there's no iron stable isotope fractionation created by the equilibration between liquid metal and iron silicate melt. So this makes core contributions, whether they're primordial core contributions or later diffusion of material from the core, unlikely scenarios to explain the isotopically light iron isotope signatures that we're seeing here. They may explain other things, but they don't account for this isotopically light iron signature here. And furthermore, we also have a problem with late accretion. And that's because we expect the bulk iron isotope composition of late accreted material to look something like chondrites, to look something like this. And yet we're down here. So we need to find another way of explaining these light iron isotope compositions that we see in the Schappenberg komatiites. Okay. So you've probably worked out by now that iron disproportionation by bridgemanite is one of my favorite ever things. So could we have a mantle plume sampling iron metal droplets generated by disproportionation in the lower mantle? Now, this might seem like a really intuitively obvious thing. We need lots of iron. We need it to be light. We want tungsten. Metal is negative for 182 tungsten, right? But here's the problem. It's not as easy as you might think. And that's because the process of metal disproportionation by bridgemanite is taking place after the cooling of our molten mantle that has already experienced extraction of iron metal to form the core. That means that our mantle already has a positive mu-182 tungsten. And so any bridgemanite that crystallizes from that will inherit that positive mu-182 tungsten. And if that wasn't bad enough, hafnium is more compatible in bridgemanite than tungsten is, so that the metal droplets that you would form by bridgemanite disproportionation should have a positive mu-182 tungsten. And yet we observe negative mu-182 tungsten. So, yet more problems. And now this brings me on to our final scenario, and we all know that it's the last hypothesis is the favorite one, right? So, of course, no surprises here, this is my favorite scenario. So we need to find a scenario where we can get the signature of iron metal formed by disproportionation, because if you recall, our experimental data tells us that bridgemanite becomes isotopically heavy, so high 57 iron being removed by a bridgemanite cumulate, and that in turn will mean that isotopically light iron, so to hop back a slide, isotopically light iron could be formed by our melt. So that sounds quite appealing, right? But we've got the problem, of course, and that problem is, of course, those droplets would be expected to inherit positive mu-182 tungsten. So we've got to find a way of creating a negative mu-182 tungsten, but giving us this highly fractionated iron isotope composition that we can't create with core material. So how are we going to do this? So, first of all, let's talk about the tungsten and neodymium isotope variations in the Schappenberg-Komatiites. They're both negative. Now, one way of creating a negative mu-182 tungsten domain in the aftermath, after core formation has ceased, if you don't want to involve metal, you can do this by really early silicate differentiation, and that's because hafnium is more compatible than tungsten such that any residual melt, so any residual magma ocean, basal magma ocean, is going to evolve to negative mu-182 tungsten. And then you might say, well, why doesn't the rest of the molten mantle, why doesn't that do this? And well, the thing is if you want to keep a mantle reservoir separate, you need to isolate it quickly. And mantle melts love reacting with ambient rock. Indeed, melt rock reaction is an entire field that has occupied many of our colleagues. So we need to isolate that domain, and the easiest way to do that is to make it really dense and really iron-rich. In other words, to make a basal magma ocean. And if you make a basal magma ocean early, you're going to give it a negative mu-182 tungsten, and you're going to give it a negative mu-142 neodymium. So we've got 2 out of our 3 isotope systems sorted out. What about the iron isotopes? So you might say, okay, brilliant. We're going to disproportionate. We're going to bring some iron metal into that basal magma ocean. And in fact, we can do the mass balance for this. We can do a really simple mixing calculation here. And in fact, we need a trivial amount of metal to account for the iron isotope composition of the Schappenberg mantle source region. So you might think, so far so good. We're doing really well here, but we now have a problem. And that problem is metal droplets. Once you get over a certain proportion of metal, and believe it or not, 1% of iron metal is over that certain proportion. Once you get over a certain proportion of metal, you are going to start segregating it. And those iron droplets are going to descend through that basal magma ocean pretty rapidly. Of course, we don't know how rapidly that is. We don't know the size of the metal droplets particularly well. We don't know the viscosity and temperature of a magma ocean particularly well. But even so, we can play around with different parameters and we get pretty rapid descent rates. So as far as we're concerned, for the Schappenberg komatiites, which erupt at 3.66 billion years, 3.66 GA, these carry the isotopic signature of disproportionation that probably happened within the first 50 million years of solar system history. And the reason why we need to do it so early on and so quickly is we obviously need to keep this negative mu-182 tungsten in our basal-rich magma ocean. That implies that we've then had crystallization of the base of the magma ocean extremely early. So how are we going to do this? Well, fortunately, and yet another reason why iron isotopes are my favorite isotope system is that iron diffuses really fast. And so we can actually do some fairly simple diffusion calculations for a range of metal droplets, a range of different temperatures. And iron isotope equilibrium between the basal magma ocean and metallic melt is going to be fast. I can't tell you hand on heart how fast, but we're talking seconds to minutes to months. And it's certainly going to be much more quick, much more rapid than the descent time of these iron droplets through the basal magma ocean. So what we have here is a mechanism where we can impart the iron isotope signature of metal droplets onto the basal magma ocean. And the reason why we can do this is that we know that there's iron isotope fractionation during Bridgmanite disproportionation, creating these isotopically light metal droplets, but we also know when we do experiments between liquid iron metal and liquid silicate that they equilibrate with no offset between the two signatures, such that the BMO is going to inherit the iron isotope composition of these metal droplets. So what we think is going on here is that disproportionation is that magma ocean crystallization to form this basal magma ocean with this negative mu-182 signature must have happened quickly, and we then think that disproportionation must also have happened super quickly, so there wasn't much time for the residual cumulate to ingrow any 182 tungsten and disturb this nice negative mu-182 signature that we have here. So now we can also use these observations to start to place constraints on the processes of magma ocean crystallization. So firstly, we've talked about this already, but the association of iron and tungsten isotopes implies a basal magma ocean, and that's because we need to dynamically isolate a reservoir. A dense melt near the core mantle boundary is the easiest way to do this, and also we need to get iron metal droplets to sink. I don't think iron metal droplets float, to sink through it. So this seems to us to be pretty compelling evidence that we actually have a basal magma ocean formed in some way, shape, or form by a middle-lower mantle, a magma ocean crystallization scenarios. We also see small negative mu-142 neodymium anomalies in these samples. These are actually much smaller than we'd expect from the presence of the 182 tungsten. You might remember it's got a much shorter half-life. And so we think one way of doing this might be either continued magma ocean crystallization or indeed unstable density stratification, potentially even melt recrystallization, dissolution, and reprecipitation processes all taking place in that first 500 million years of the Earth's history. And these would serve to kind of mute, to sort of rework the mu-142 neodymium isotope signature here. And of course, we have this decoupling in our long-lived hafnium and neodymium isotopes. And this suggests that at least for the particular rock suites that I've talked about, that we're looking at Bridgmanite cumulates that record dominantly time-integrated, quite shallow magma ocean crystallization processes. That's because of the decoupling between hafnium and neodymium isotopes is pressure sensitive, and generally it ceases to exist at pressures above about 90 gigapascals. So we can say something about magma ocean crystallization here, And now we can kind of start thinking about the relationships between these different groups here that I've covered. So here are the ISOA samples, 3.72 GA. Here are our Schappenberg samples, 3.55 GA here. And they're both sampling components that were formed in the first 50 million years of solar system history. Here is our poor forgotten child. Here is Veltevreden. No tungsten isotope data for Veltevreden, but 142 neodymium. Veltevreden seems to lie between these end members that we've isolated from the ISOA sample suite and the Schappenberg mantle suite. Veltevreden's also a much younger komatiite suite here. So if you have a younger komatiite suite that potentially represents mixing between these two M members, then obviously we had to have formed these two M members, which thus tells us that potentially that basal magma ocean crystallization and M member formation was complete well before the formation of this komatiite series here, and we then need some kind of process that it would have allowed these isotopic signatures to become homogenized. And indeed, it's this homogenization process. This is an example of 142 neodymium isotope anomalies seen in terrestrial samples through time. We can actually see the evidence of mixing between terrestrial reservoirs and the progressive decrease in 142 neodymium, and you also see this in tungsten, isotopic heterogeneity through time. And indeed, perhaps one of the reasons why we don't see signatures such as these negative mu 182 neodymium signatures either in the ancient mafic rock record or even at all in the modern record is that the entrainment of dense basal magma ocean material is going to be extremely difficult and only possible in extremely hot mantle plumes. So I'm going to leave things here now, and I'm going to say that hopefully, I've convinced you that we can use these different iron isotope signatures in komatiites and metabasalts, and we can go a step beyond simply identifying the presence of ancient components and the presence of magma ocean crystallization. And maybe we're just on the very cusp of being able to start to think about can we actually gain some insights into the processes of magma ocean crystallization on Earth and oxidation on Earth, and potentially also on other planets in the future. And so with that, I will thank my collaborators once again, and of course, thank you all for coming here and for listening.
Thanks, Helen, for this wonderful talk. That was really fascinating. So we have time for some questions. It's hard to see, actually. So if you have a question, please come to the microphone. I can probably start with a question, actually. Okay. So if I get this right, if we think about a basal magma ocean, we immediately kind of consider that it's there, it's more dense, so it has more iron in it, right? So it sits there at the bottom of the mantle because it has more iron in it. And then, of course, once something dense like that has been made, it's hard for it to sort of like disappear. And of course, there is then the same argument follows with large low shear velocity provinces, that if they've been there for such a long time, the possibility is that they are dense and they have a lot of iron in them. So, but what's very interesting about what you say is that you're arguing that whatever this signal is has disappeared. And yet people would still argue that there is some signals that are coming from large low shear velocity provinces because they argue that plumes come from outside. But so would you argue that large low shear velocity provinces shouldn't have any connection anymore to a basal magma ocean because we just don't see those signals anymore?
So that's a really interesting question, and it's a little hard to unpick that because obviously, you've got the effect of decreasing mantle potential temperature through time. So you are going to be less and less easily able to sample this dense material. So I'm not a geophysicist and I'm not a mineral physicist either. So my take on it would be that the size of the basal magma ocean has shrunk. Maybe it's entirely crystallized. Potentially some of these cumulate reservoirs have been reworked and are now sampled in mantle plumes. But I would suspect, because we see these are pretty big, these low velocity anomalies, I would expect that some of them still reflect the accumulation of either crystal piles or even maybe very dense interstitial melt present. And then, of course, you have dense material. You might then have the accumulation of recycled oceanic crustal material joining them as well. So it's a bit hard to pull that out entirely, but I'd be extremely surprised if some of that low shear velocity province material, some of that material was not residual material from magma ocean crystallization.
Yeah, we do have some questions. Sorry, I didn't see that because the lights are so bright here. Yeah, please go ahead.
Okay. Hi, Helen. Thanks for this. It's really nice to get this complete image of the basal magma ocean. I was wondering about these iron droplets because you were mentioning the size of them. They're very tiny, and I know that iron diffuses really fast. But have you thought about the distribution of these necessary to actually affect the entire iron isotope fingerprint of these komatites?
Sure. So I can only really talk about the iron isotope composition of the source region of these particular komatites. So I can't talk about the basal magma ocean as a whole. Now one could argue that maybe there's a heterogeneous concentration of iron metal droplets in that particular region of basal magma ocean for whatever region, and that the Schappenberg source is really unusual. We could also argue that because dense basal magma ocean material is going to be really hard to entrain by a plume, that maybe Schappenberg was a plume, perhaps it was unusually hot, so it was able to entrain this dense material. Or we could say, well, perhaps we actually also entrain some bridgemanite cumulate material, which will be less dense. It'll be the equivalent of a Harzbergite in a mantle plume, counterbalancing the peroxenite component. It won't melt anywhere like as easily, so you won't see its isotopic fingerprint, but it's responsible for helping you get the material up. So it's hard to say whether, so right now, I don't think we can talk about distribution of iron metal droplets in the basal magma ocean as a whole and say how representative it is. I think we can say that this is a scenario that works for one particular komatiite suite. Maybe in the future there will be other komatiite suites where you see these signals, and then we can start to think about global or basal magma ocean-wide processes.
Thanks.
Thank you. Hi. Oh my God. That was much louder than I thought it was going to be. Georgi Mahatadze, IPGP. I have a question. Thank you very much for your talk. So the accretion history of the Earth, we don't really know it, I guess, as a community. And at least some scenarios of the accretion history, in my understanding, allow for proto-Earth accreting. We have magma ocean. Maybe it was full depth, maybe it wasn't. Then some time passes, then we have giant impact, and we have magma ocean again, maybe again full depth, maybe again not. So how much more complicated does it get when we think about this?
Would you like to review my next grant proposal? The simple answer is I don't know. In this particular lecture, I've talked about a magma ocean in the aftermath of the moon-forming giant impact to keep things simple. But it's not impossible that you had magma ocean events on the proto-Earth. And that you may even, if that proto-Earth was large enough, that you even had a basal magma ocean on the proto-Earth, and that during the moon-forming giant impact, that material became highly compressed, but not completely rehomogenized through the mantle. That's entirely possible. And I don't know how to find that out. So if you have ideas, I would really love to talk to you about that.
Thank you very much.
Hi, Helen. Thanks. Oh, it was loud. Thanks for the great talk. I really like this model because, as you probably know, the Schappenberg komatiites have this kind of freakishly low, highly siderophile element abundance that you don't see in other komatiites. So I think potentially equilibrating with those iron metal droplets can help explain that. But correct me if I'm wrong, if I remember rightly, they also have fairly elevated tungsten compared to similarly incompatible elements, and tungsten's moderately siderophile. So how do you reconcile that with a melt that's equilibrated with lots of iron?
That's a really good question. So I guess we're used to thinking about tungsten as being siderophile, so we're used to thinking about the Earth's mantle being stripped of tungsten in the aftermath of the moon-forming giant impact. Truthfully, I don't know the answer to your question, but I guess I could hypothesize and say that if you did have iron metal disproportionation in the lower mantle, well, I'll correct that, I think you do have iron metal disproportionation in the lower mantle, then any tungsten that you have there is going to go into those metal droplets. Now, I don't know, there was a really interesting talk yesterday from Igor Putel about the Schappenberg source, about what might be going on there. Potentially there's something else really unusual going on about its particular source. But I think possibly we're looking at the decoupling of tungsten, which is only moderately siderophile, from the other highly siderophile elements.
Thank you very much.
Professor Williams, it was a very insightful talk actually. So I just have a basic question regarding the core mantle boundary. So I just want to know, is it chemically evolving since the early Earth, or is it representing the record of 4.5 billion year old Earth? So what do you have the view on it?
I'm not quite sure I understood your question, to be honest. Would you mind repeating that?
Yeah, so it's about the core mantle boundary. So as you said, BMOs are crystallized in and locked in the heterogeneous mantle. So is the core mantle boundaries still evolving chemically, or is
is the core mantle boundary still evolving? Very good question.
Okay.
I don't know if anyone knows, to be really honest with that. I certainly don't. I believe, certainly my mineral physicist collaborators tell me that they think that the Earth's basal magma ocean has completely crystallized by now.
Okay.
And the question that is occupying them now is whether, from the InSight mission on Mars, that potentially that's not been the case on Mars, and there might be a fundamental difference between Mars and the Earth in terms of the evolution of the core mantle boundary. But truthfully, I think we don't know. I think this is a real challenge for our community.
Okay, thank you.
Okay, I think if there are no other questions, then I would say that afterwards now is Meet the Plenary, and the Meet the Plenary is pretty full, but there probably is one or two positions still available. So if you didn't register but you'd still like to go to the Meet the Plenary, then please just come to the front here, and then you can go along to the Meet the Plenary. So let's thank Helen one more time for this wonderful talk.